might realize.
You gotta say got it.
Got it.
All right.
Oh no, I can't see where that is.
Your mouse is gonna be on the other.
Oh yeah, I have to like navigate it in. There we go. Got it. I don't want to leave meeting. Okay. Specifically, I want to talk about how thunderstorms might realize less of their cape in the future climate. So, how many of you know what cape is? Okay. Jim didn't raise his hand, so I'm going to explain it.
I've been here for a long time. I don't really know what cape is.
So, sort of an analogy to, you lift an object up. It has potential energy. You release it, it accelerates toward the ground. It takes that potential energy, converts it to kinetic energy. Cape is kind of the same thing, but in the opposite direction. So if you have a chunk of air that is lifted in the atmosphere and it can become positively buoyant, the cape describes the potential energy associated with that positive buoyancy. And if the certain conditions were met, all the cape would be converted into kinetic energy as a chunk of air rose through a thunderstorm. How many of you have seen skew T diagrams? Some people really hate skew T diagrams. So I didn't want to offend anybody, but I personally like them. And I think it's a nice way of visualizing cape. So
Right, we're not in England where they use the stew or whatever.
oh no, I'm not even talking about that. Like some people just want like plot the temperature as a function of height. I'm just like, well, it goes way over to the left side. So we can visualize cape on skew T diagram. So we got temperature on the x-axis, pressure on the y-axis. This profile here is this red line is the temperature.
You might have put
I did click.
that's a clicker.
Okay, I'm not going to use that thing. I'm just going to use my hands. So this is the temperature of some environment. Say we launch a balloon. We're trying to figure out whether an environment is going to support thunderstorms. So we launch a balloon, we get the temperature. Oh, we got a stick. That's this red line right here. Just if you're curious, the green line is the dew point. And this black line right here is the temperature of an air parcel that we lift from the surface. And you can see on this diagram, it's to the right of the environmental temperature. So it's going to be warmer than its surroundings. It's going to be positively buoyant. So we say that the air parcel has cape. And if it did follow this path right here, it would realize all of that potential energy as kinetic energy by the time it got to this point right there. And there are a bunch of assumptions we make when we go through this theoretical exercise of saying is there cape. And one of them is we assume that this air parcel doesn't mix with its surroundings. So that's something we're going to talk about quite a bit today. So it's difficult to understand how thunderstorms might change in a future climate, but one thing we can tell is that cape will increase. And we see this in climate models. We also can show this through relatively simple theoretical exercises. So just as one example, this paper by Dave Romps in 2016 basically shows that cape scales with the Clausius-Clapeyron relationship. What I mean by that is, okay, the Clausius-Clapeyron relationship says that the moisture carrying capacity of the air is a nonlinear function of temperature. Temperature goes up, we can hold way more water in the air. So that's shown by this this dashed red curve right there. So the y-axis here also has cape. So what this article said is that the dependency of cape on temperature in the tropics should follow that Clausius-Clapeyron relationship. So the amount of water that the air can hold goes up by 6 to 7% per degree Kelvin. Cape should go up at a commensurate rate. So what this tells us is as the climate gets warmer in the tropics, we should have a lot more cape simply because the air can hold more water vapor. And a lot of people have used this to speculate, particularly in the mid-latitudes, that storms might become more intense in a future climate. So we have more available energy to convert into kinetic energy in a thunderstorm updraft. Stronger thunderstorm updrafts are associated with increased rainfall, increased lightning, potentially more damaging hail. You might end up with more severe weather out of a storm that has a stronger updraft. So this suggests that we might end up with stronger storms in a future climate. One of the things that doesn't get discussed a lot in this context, though, is entrainment. So what I mean by entrainment is I have a photograph here of a cumulonimbus cloud. So this is thunderstorm. When we're talking about cape, we're talking about this air that comes from the boundary layer that has a lot of cape. It has a lot of potential energy. And then that air will go through the center of a thunderstorm updraft and make it to the upper troposphere. And the sort of release of that potential energy is what drives and the realization of buoyancy is what drives the upward motion and updrafts and thunderstorm updrafts. But the clouds will also ingest a lot of dry air from the surrounding free troposphere through a process called entrainment. That's going to actually dilute the buoyancy in the core of the cloud. It's going to make us realize less of our cape than we otherwise would have if that entrainment weren't there. And then just going back to the skew-T diagram. So this was the undiluted parcel, meaning that it doesn't experience any entrainment. This is the theoretical vertical velocity profile you get from that undiluted air parcel. And then as I just animate this, I'm gradually increasing the entrainment rate. You see the temperature pretty quickly goes down as the entrainment rate goes up. And graphically, CAPE is represented by the area between this lifted parcel curve and the environmental temperature. And that area goes down dramatically as the entrainment rate goes up. So what this shows is that entrainment is really strongly regulating how much of that CAPE we're actually realizing. And you can see it over here with the vertical velocity profile too. As the entrainment rate goes up, we start with this really kind of scary vertical velocity profile, and then it quickly goes down towards something that's a lot more meager. The theoretical cloud top, where the vertical velocity goes to 0, goes down in the atmosphere too. Something that's going to be important later, something that we know about entrainment, is that it really depends on cloud width. And this is something that Ed and I were just talking about. Ed has shown this through his past work. One of the first people that discussed this extensively in the context of deep convection. So what I'm showing here are just two simulations of really idealized thunderstorm. What's on the y-axis is height. The shading is air vertical velocity. So the blue is upward motion, the reds are downward motion. And these are both the same, except I'm forcing a smaller cloud to form over here and a bigger cloud to form over here. And you can see this updraft is kind of dinky. So the blues, again, are upward motion, and it breaks down into these individual pulses. We call that a thermal chain. Doesn't get much above 7 kilometers. All else is the same here, except we're just forcing a wider updraft to form, and it becomes this comparatively vertically continuous sort of really hefty updraft that makes it all the way to the upper troposphere. It doesn't have that breakdown into individual pulses. So the wider the cloud we have, the less detrimental the effects of entrainment are. Lots of times we say that the entrainment rate is lower. What we're really talking about there is the fractional entrainment rate, but we'll just say entrainment is lower when updrafts are wider, and that will become important later. Okay, so why is entrainment important? You probably sort of figured it out from here. But just to reiterate it, it sort of regulates this efficiency of converting CAPE into kinetic energy in storms. And we can see that in our current climate by just looking at storms in different environments. For instance, these are radar wind profiler observations of the vertical velocities in convection in the Amazon. And the peak vertical velocities. Oh, that was not. But I said something that offended somebody. You see it? How's it going?
Started early.
Yeah, so these I think you might have already seen what I've talked about so far anyway, so you didn't miss it. So 15 meter per second vertical velocities in convection in the Amazon. Generally in the tropics, we see vertical velocities and maybe peak 30 meters per second in tropical convection. If you look at the CAPE in those environments, that would support updrafts vertical velocity to 50 to 70 meters per second. So in the tropics in general, we have a really poor conversion rate of CAPE into kinetic energy. It's 10 to 20%. The reason for that is tropical deep convective updrafts are relatively narrow. They have pretty high fractional entrainment rates, so they get really diluted and they don't realize all of their CAPE. They only realize a small fraction of it. But the same cannot be said about convection everywhere. Another sort of extreme example are supercell thunderstorms. So this is a simulation from a recent study of mine where I was actually looking at mesocyclone and tornado dynamics, but it's a sort of nice illustration of the point I'm trying to make. So this is sort of a simulated what a radar would see if this were listed. What's noteworthy from this simulation is that the profile I used to initialize a simulation, the square root of 2 times CAPE is 60 meters per second, but the updraft maximum velocities were regularly 75 meters per second. So this is 145% conversion rate of CAPE into kinetic energy. I won't get into the details of why that's more than 100%, but suffice it to say, supercell updrafts are really wide. They're an order of magnitude wider than tropical deep convective updrafts. And the air that goes through the center is basically undiluted. So you're realizing all of your cape and supercells because they have small fractional entrainment rates. You're realizing only a small fraction of your cape and most of the other convection that happens on Earth. And what this demonstrates is entrainment really strongly controls how strong storms can get. This one exists in less cape than the storms in the Amazon, but it has a much stronger updraft. So today, I'm going to ask the fundamental question, like, should the efficiency that I'm talking about of converting cape into kinetic energy change in a warmer climate? Should it depend on temperature? This is the first thing I'm going to talk about today. And to design an experiment to address this, it's relatively simple. Just create synthetic atmospheric environments where I hold the cape constant and change the temperature of the entire profile and see whether the entrainment effects become more detrimental at warmer temperatures. So this is another SKU-T diagram. I'll go back and let it animate again, and you can see I'm sort of pulling the entire profile over to the right, so I'm increasing the temperature of the entire profile. But the shaded area in here, which is the cape for an undiluted parcel, staying the same. And what I'm trying to see is, okay, as we get toward warmer temperatures, does the efficiency of converting that cape into kinetic energy change? And what I'm going to do is, okay, so this, again, that black line is an undiluted parcel. I'm also going to, over a range of these environments, lift parcels that experience entrainment and see if their buoyancy goes down. And actually, what I'm going to look at is the sort of cape of those entraining parcels, which I'll call entraining cape. I can also do things with this experimental setup, like mess around with the free-tropospheric relative humidity. Generally, this is something that entrainment is dependent on. When the free troposphere is moist, entrainment effects are less pronounced. And when it's dry, entrainment effects are more pronounced. So I also want to see if there's some dependency on this free tropospheric relative humidity. Now I'm just going to look at a range of temperatures. And so I sort of regulate the temperature of this entire profile by changing the surface temperature. And I'll look at a range of surface temperatures from 285 Kelvin to 310 Kelvin. That's much wider than the range if you go from like pre-industrial typical convective environmental temperatures to what we expect in the worst case scenario toward the end of the 21st of the 20. How do you say like the first 100 years in the 20th century? How do you say that?
The 21st century.
Yeah, but that's the entire century. Anyway, you get what I mean.
Good luck.
So I'm trying to look at a wide range of temperatures, because really just on a fundamental understanding, on a fundamental level, I want to understand how entrainment is affected by temperature. Okay, so I'm going to change the temperature. I'm going to hold the cape constant. The cape is represented by this lighter red shading in the background. And how much of that cape we're actually getting is represented by this darker shaded area. That's the entraining cape. So as that area goes down or up, that is telling us how the efficiency of converting cape into kinetic energy goes down or up. So here we're warming things up, and you can see that shaded area goes way down to the point where we get to these really warm temperatures, we're basically getting nothing. So if I just animate this once more, on the top, I have the entraining cape. So if this is 1,000, our undiluted cape is 2,000, we're getting 50% at the cooler temperatures.
John, how are you calculating the entrainment cape?
It's just like an entraining parcel model. So you assume you have the entrainment rate is constant. So you assume that there's a constant mixing rate along the parcel as it ascends.
Okay.
So what's driving the changes in the buoyancy you're actually getting is because the temperature of the environment is changing. And the environmental relative humidity is actually held constant here too.
So you're assuming as you change the temperature, you still have a 1 kilometer updraft regardless.
Right. It's just like, it's theoretical exercise, like all else being equal, how should entrainment depend on temperature? And I mean, you asked me this question at mesoscale. We don't really know how updraft radius might change in a future climate. So that's like a whole nother dimension of the problem.
So you mean a constant fractional rate?
Constant fractional entrainment rate, yeah. Okay, so you can see this just kind of go away, which means that our efficiency of converting cape into kinetic energy is going way down. Play another game here though, and say, okay, I want to keep the E cape constant. So say I have a storm in this cold environment, How much Cape do I need in a warmer environment to have an equally intense storm? So now the darker shading could stay the same, but the lighter shading, the actual Cape might change. And then you can see the changes quantitatively up here. So we start with 2,000 joules per kilogram to have a certain intensity of a storm in a cool environment. By the time we get to a warmer environment, we need more than double the Cape to have a storm of equal intensity because we're so much less efficient at converting Cape into kinetic energy. Okay. So I can sort of summarize this. I only showed you an example over a narrow range of parameter space, but I can summarize this by looking at, okay, on the x-axis here, we have surface temperature. So we're warmer climates on the right, cooler climates on the left. The y-axis here, this is free-tropospheric relative humidity. And the shading here is our efficiency of converting Cape into kinetic energy. That's how much Cape we get. And basically, we get the least Cape when we're in a warmer environment and it's really dry. And we get the most Cape in a cooler environment and it's really moist. And this is relevant that its sensitivity of how much Cape we're actually getting as kinetic energy is more pronounced at drier environments. So sort of like Intermountain West and high plains environments where we do have a pretty dry free troposphere. But in general, it's sort of, you know, in the convection community, we talk a lot about how relative humidity affects entrainment. And this temperature effect, at least over the range of temperatures we're looking at here, is pretty much similar in terms of how much it changes how much of our Cape we're actually realizing, or how as you go toward warmer temperatures, you make the entrainment effects much more detrimental in the same way that as you go toward a drier environment, you make the entrainment effects much more detrimental. What's the reason for this? It's sort of complicated, but it can be kind of encapsulated in a relatively simple demonstration here. So what I'm showing you here are profiles of moist static energy. Has anyone heard of moist static energy? I saw like, yeah, okay. What about theta E, equivalent potential temperature? Okay. Same thing. For this purpose, they're the same thing, basically. We have BAM's article coming out that talks about this. But so this is moist static energy. So it's like a theta E profile. The cool environment is the blue right here. The warm environment is the red right there. And these both have the same Cape. Okay. So what this shows us is that in warmer environments, the difference in moist static energy between the air that has the Cape and the free troposphere above is much larger. That means we have much more room to get diluted by entrainment. So if I add in the entraining curves right here, this is a parcel lifted from the surface that experiences entrainment. That parcel, his moist static energy is approximately conserved for an adiabatic parcel. So when you have entrainment, it's just sort of diluted as if it were a passive tracer. It relaxes back to the environmental temperature. And in the warmer environment, it's got much further to relax to. So basically, because of the nonlinear nature of the Clausius-Clapeyron relationship, we just make this difference in moist static energy, or theta E, between the lower troposphere and the sort of upper free troposphere much larger. So parcels get much more diluted because of that. All right, I'm just playing around with theoretical models, simple parcel models. Is this just hold in simulations? So we're submitting a paper to Journal of Climate in like a week or two that has a much more thorough analysis of these simulations, but I can just show you a simple comparison of two. On the left, we have a cool environment. This is 295K. All right, this is 305K. And what I'm just showing you is a vertical profile of buoyancy. You can already see that. So we put random noise in these simulations. We don't put any wind in. It's really simple, just bubble release. But you get less buoyancy on the right-hand side. And the Cape in both of these simulations is the same. And it turns out the simulations really fit well with the theoretical predictions on how entrainment should depend on temperature. And okay, circling back to like, we expect Cape to increase in a warmer climate. So here from that ROMP study I talked about, this is like the curve for how Cape should depend on temperature. Here's a sort of theoretical curve from this study. How much of an increase in Cape is needed to maintain a storm of a constant intent? Sorry, I messed up with that sentence. How much of an increase in Cape do we need with temperature to maintain a storm that's of constant intensity? And the curves are pretty close to one another. So it suggests that a lot of the increase in Cape that we get at warmer temperatures might be compensated by less efficiency in getting that cape and converting it into kinetic energy. So it's, at the least, says we need to be including this entrainment in this narrative when we're talking about how storms might change in future climate. Particularly if we look at climate models and we look at increases in cape and say, hey, storms are going to become more intense, we need to be accounting for how entrainment is affecting that cape. Just a few side things that I haven't talked about much. These effects are much more pronounced for relatively narrow updrafts. As you get toward the wider updrafts like supercells, where I said undiluted parcels go through the middle of supercells, they don't care about entrainment. So supercells might get more intense in a warmer climate. Tropical convection might not, or might increase in its intensity at much less of a rate because of that. There's a little bit of a parallel here between what we're talking about here in general deep convection and what people talk about in the tropical cyclone community, where storms might get more intense but less frequent in future climates. We might see more intense severe thunderstorms because when they become supercells, they don't care about entrainment, but they might become less frequent because they're harder to initiate, which is what I'm going to talk about next. All right, so I just want to say a few things, maybe more than a few things, but not a lot of things, about how this might affect the initiation of thunderstorms. So here's like sort of an application of the really theoretical basic stuff I just talked about. To initiate thunderstorms is this really important interaction between vertical wind shear, and I'm talking about severe thunderstorms in the central US. It's a really important interaction between vertical wind shear and entrainment that plays a role in that initiation. So for instance, I'm showing 3 different simulations right here. These are like vertical cross sections again, and what's shaded is going to be the cloud regions. No shear, moderate shear, strong shear. You can see in shear environment, we initially have shallower updrafts, but as the simulation goes on, we develop this really steady, longer-lived, deeper and more intense updraft. So the relationship between shear and convection is really complicated. It seemed like maybe it was a little harder to initiate the storm over here, but once it got going, it was much stronger. And we just changed the initial conditions slightly though, and we get this, where you have trouble getting going and then the storms basically die in the stronger sheared environment. Whereas in the less sheared environment, we have more intense storms. So there's a really strong sort of nonlinear dependence on, the environment that you're trying to initiate a storm in and whether or not it can get going and turn into a bona fide severe thunderstorm. The reason I'm talking about this is because it relates back to the entrainment effects that I've already discussed. This nonlinear relationship here is really dependent on entrainment, as I'll show. And just another simple demonstration of the nonlinearity here. These are all the same simulations. They have shear. And all I'm changing is the forcing region that I'm using to initiate a cloud. So here's the radius of the forcing region. It goes up by intervals of 100 meters. And okay, there's only 100-meter difference in that forcing radius between these two simulations here, and you get a supercell here, and you don't get anything here. The convection basically dies. So there's basically a bifurcation in the outcomes. If you don't have a forcing radius that's large enough, you can't get a storm to get going. So I spent several years of my career trying to understand this behavior. And okay, we can see it encapsulated over a bunch of simulations here. During the initial part of simulations, this is cloud depth. These curves are for sheared simulations, and the color is the radius of the initial forcing I'm using to try to make clouds. So the darker colors are wider initial forcing. Same thing here, but with no shear. The non-sheared storms get much deeper earlier on. There's like a suppression of the growth of initially of the sheared storms. As we go later in the simulations, okay, with the smaller initial forcing radius, we basically get nothing in the sheared environment. But with a larger initial forcing radius, the storms grow much deeper and they all kind of evolve toward this relatively steady updraft depth. I spent years scratching my head trying to understand why this would happen, why convection would behave this way. And I guess the clue I got into understanding it was, this is a relatively dry environment, the first one I showed you. Now I'm showing you the same curves in a relatively moist environment. And the thing that you'll note is that these simulations where I just couldn't get anything going, basically all of those became supercells once I increased the relative humidity. And what this told me is that what's going on here is related to entrainment. as I increase the relative humidity, the negative effects of entrainment get less pronounced. And the storms that struggled in the dry environment to get going actually are able to get going in the moisture environment. So I came up with a hypothesis for this, and I call this a progressive routing hypothesis. And I'm going to demonstrate it here using really crappy PowerPoint cartoon graphics. So we got vertical wind shear in the background. I don't really know why the arrows are showing up so sort of faded, but what I'm trying to show you here is a vertical profile of ground relative wind. Okay, and it's increasing in speed with height, which means we have vertical wind shear. And here's a cloud that's just trying to develop in this environment. Say you have a air mass boundary or a boundary layer thermal that's trying to trigger a cloud, and a cloud starts to form. What's going to happen in this cloud? It's going to get blown downstream by the ambient wind. And the speed at which it moves downstream is going to be something like the average wind speed through the depth of the cloud. So graphically, I'm representing that speed by this arrow right here. That's what the speed of the storm is relative to the ground relative wind vectors. So the storm relative speed are these, especially in the lower atmosphere, are these red arrows right here. I'm just taking these ground relative vectors and I'm subtracting the storm motion. So I get the storm relative vectors here. So basically what this storm does by getting advected downstream is it creates its own inflow because it's moving relative to the background wind. If this inflow is sufficiently strong that it drives enough mass into the base of the storm that wants to make it wider. And as I said earlier, wider storms are less susceptible to the effects of entrainment. The cloud is going to get deeper because it's experiencing less detrimental entrainment effects. If it gets deeper, it starts tapping into this stronger flow aloft, which is going to want to blow it faster downstream, which means its motion vector is now this longer arrow, and its low-level cloud relative vectors are now these longer red arrows. So we're driving more inflow into the storm. And that, because we're driving more inflow, we're driving more mass into the base of the storm, which is going to want to make it even wider, which allows it to get even deeper because now that it's wider, it's even feeling the effects of entrainment even less. And eventually, basically, the cloud grows until it hits the tropopause. So here we're moving really fast downstream because we've tapped into this really strong steering flow aloft. And we have really strong inflow that's giving the storm enough mass of air that has really high cape that can sort of sustain itself. But you have to start with a wide enough initial radius. And if that doesn't happen, the inflow that you drive with this initial cloud motion isn't strong enough and it just sort of dies. So this was my explanation for what explains the sort of bifurcation and outcomes that I talked about earlier, why whether or not you can get a severe thunderstorm is so strongly non-linearly dependent on the initial conditions. Okay, so I wanted to test this through a series of the simulations I showed you earlier. First thing I wanted to see is as clouds get deeper, does their cloud relative flow increase? So remember, that was a key part of this hypothesis here, that as clouds are getting deeper and wider, they're moving downstream faster and they're driving more cloud relative flow. Okay, these are just time series of cloud depth on the x-axis and cloud relative flow on the y-axis, and they basically form a line, which shows that they're really strongly correlated with one another. Are the deeper clouds wider clouds? That was another key part of this hypothesis. So we got cloud depth on the x-axis, cloud radius on the y-axis, and yes, the deeper clouds are the wider ones. So as clouds get wider, they're getting deeper. And to really encapsulate this whole thing, I built this theoretical model that encapsulates essentially this progressive routing hypothesis. One of my co-authors called it the hypothesis in gory details of the hypothesis. I know he said it in his talk. I'm not conveying it well here, but essentially you give a parcel model like the one I told you about, Jim, an initial radius, and you can compute its entrainment rate from that, an initial thermodynamic profile. That gives you a profile of vertical velocity, which tells you how deep a cloud gets, because you can just figure out what cloud top is by where vertical velocity goes to 0. You know the depth of the cloud, you can estimate its advective cloud motion. With the advective cloud motion, you can estimate the low-level cloud relative flow. Using mass continuity, you can predict what the new radius should be. And with the new radius, you can figure out what the new entrainment rate should be and go back to this first step and repredict the vertical velocity, which will give you a new cloud depth. And basically, the theoretical model keeps going through this circular loop and predicts an outcome based on an initial radius and initial thermodynamic profile. And the outcome is, can we get a sustained thunderstorm or not? So I'm just visualizing this here. I'm going to animate this and basically just pay attention to this center one right here. This is cloud depth from the theoretical model. Remember, the colors, like what I showed earlier, are represent the initial sort of radius that I'm giving the theoretical model. So these bluer colors, I'm giving it like a smaller forcing radius to start a cloud. The redder colors, I'm giving it a larger forcing radius. And I'm going to start with no shear, and then I'm going to animate it and sort of increase the shear magnitude. Eventually, you get this change in behavior where wide enough initial radii all evolve toward this common steady state, and initial radii that are insufficiently wide end up just essentially decaying and not developing a supercell thunderstorm. So this theoretical model, which is relatively simple, it was maybe like 1,000 lines of computer code. I don't know, that doesn't make it sound simple, but compared to like the simulations I'm running that have like the full physics of the atmosphere, this is a much more simplified version of what's going on. Actually replicates the behavior of what was going on in the simulations. And the one more thing I want to see is, okay, this is a relatively dry environment with 45% relative humidity. In the simulations, when I increased the relative humidity, it became easier to get a storm. A smaller initial forcing radius would make a supercell thunderstorm develop. So what happens when I increase the relative humidity in this theoretical model? The relative humidity is going up, and you see some of these curves that represented dying storms are jumping over to storms that end up turning into sustained supercells. So basically, with relative humidity being larger, you get more of these initial storms. You need less of an initial radius of forcing to get a supercell thunderstorm. It becomes easier to get a sustained thunderstorm. So basically, this theoretical model that was built based on the hypothesis behaved in a very similar way to the simulations, which really supported the hypothesis or supported the hypothesized mechanism as an explanation for what was going on in the simulations. So we have a two-part study, and I actually forgot to put it in here. We have a two-part study that talks about this that came out in JAZ last year, if you're interested. But I want to just, to close today, bring this back to the context of what I talked about earlier, how entrainment effects might influence thunderstorms differently in a warmer climate. Okay, so what this theory basically tells us is that we need a critical forcing radius to get a supercell thunderstorm to develop. If you don't have that, it can't happen. So going back to looking at a range of temperatures and how things behave over a range of temperatures. Now here I'm showing the radius from my theoretical model, and we have this bifurcating behavior where, okay, so if your initial forcing radius is above roughly 2 kilometers, you get supercells that form. They all sort of evolve toward a common steady state radius. And if it's below that, you can't get a sustained storm to develop. And this is at a surface temperature of 296 Kelvin. If I increase the surface temperature, basically that threshold radius above what you can get a supercell and below what you can't goes up from somewhere on the order of 2 kilometers to something like 3.5 kilometers. I have a numerical modeling experiment planned to further address this idea, but what this tells me is that in a warmer environment, it's harder to trigger a supercell. It's harder to incite the process that actually grows like a sort of dinky initial, when we're chasing, we call them turkey towers. These initial tries at forming deep convection, they have to, through this progressive rooting process, grow and get wider with time and turn into a supercell thunderstorm. And you need that initial turkey tower, that initial attempt at making an updraft to be wide enough. And if it's not, you can't get a supercell. And the threshold radius you need for that to happen goes up in a warmer climate because of the entrainment effects I discussed earlier. So there's some evidence in dynamically downscaled simulations of GCMs. So global climate models, we simulate future climate scenarios at a relatively coarse resolution, typically greater than 10 kilometers grid spacing between grid points. So you can't explicitly simulate thunderstorms. But people will take those climate model simulations and put something like the weather research and forecasting model, the WRF model, in them and simulate part of that global climate model run at much higher resolution to understand how storms might behave in a future climate. There's some evidence from these downscale simulations that storms might get harder to initiate, but once they do form, they become more intense. And I'm sort of proposing this as a contributing mechanism to that trend, that it might get harder to initiate severe thunderstorms because you need more of a push to get them going. So what gets severe thunderstorms going? It's air mass boundaries. So outflow boundaries, the dry line, something like that. The dry line needs to have a stronger circulation to actually initiate a thunderstorm and get it going in a warmer climate than it does in a cooler climate. But because there's more CAPE, once a storm does get going and it gets to the point where it's a wide supercell updraft and it's got a 100% efficiency rating, 100% efficiency of converting CAPE into kinetic energy, might end up being a more intense supercell than what we experience in current climates. And true to form, I get to my conclusion slide and like halfway through discussing it, actually realize it's my conclusion slide. But yeah, I guess I sort of just summarized what my conclusions were related to this. This is just like, you know, I basically made these curves over the last couple of days. I have a planned study where I'm going to go through like a range of like simulating updrafts with a range of initial forcing radii and over a range of temperatures to see whether simulations actually behave this way. But what I'm really trying to start here is a narrative and encourage scientists that are looking at how thunderstorms might change in future climate to account for entrainment effects, because they're very important in A, determining how intense thunderstorms might be, and B, determining whether or not they can initiate in the first place. So yeah, I guess with that, I'm done. So if anybody has any questions, go for it.
I know that you are fully aware of this and you've emphasized the importance of the diameter of updraft.
Mhm.
So, you know, I know very well that you appreciate very, very much the importance of that. But it seems to me as though, for the most part, the modeling that you're doing is giving us a great variety of looking at the different animals in the convective zoo and not spending very much time on what truly determines the existence of the elephant in the room, which is the updraft diameter. What it depends on. I don't think I heard you mention boundary layer depth.
So this is an explicit theoretical prediction of updraft radius. Here.
I'm sorry.
This is an explicit theoretical prediction of updraft radius.
Yeah.
So in this theoretical model, it depends on the vertical wind shear. And so I've done some theoretical work that shows, and I think the real question is, you know, you talked about the LCL height. You know, I think in weakly sheared environments, things like the LCL height or this sort of scale of lifting along the edge of an air mass boundary are primarily controlling how wide clouds get. Once you get over a certain threshold of shear, it's the shear that determines it through this sort of process here. Because like, you know, these larger radii, they all evolve toward a common updraft radius that's determined by the magnitude of the vertical wind shear sort of coupled with thermodynamic environment. And it's the reason for that is this mass flux argument. You have a certain amount of inflow and that has to sustain a certain amount of vertical mass flux in the updraft. And there are thermodynamic constraints on the vertical velocity. So mass continuity can tell us what the radius should be, those things coupled. But I think that the thing that I don't understand is where you go from shear being important and what's controlling updraft radius to some other things being important. Mm-hmm.
Okay, so through all this, the entraining rate we're looking at is the fractional rate.
Mm-hmm. Yes.
Which is cross-sectional cloud area and vertical mass flux.
Yes, it's think about it like, it's a little confusing because we always talk about entrainment rate, but we really mean fractional entrainment rate. Fractional entrainment rate is the rate with height at which the core mass flux is diluted. So fractional entrainment rate is actually dilution, not entrainment. And I'm guilty of, I mean, in this talk, I'm guilty of just calling it entrainment, but it should really be the fractional dilution rate.
Okay, so then just kind of following up on that.
Yeah.
Right, in order to increase the efficiency of a conductive tower, you don't want any dilution.
Mhm.
And to me, it kind of seems like, all right, that means you want cloudy air that is going to insulate before
Mhm,
any air that literally entrains air
mhm.
isn't going to penetrate deep enough to it.
Right.
But you kind of showed how that's such a heavy dependence on relative humidity.
Yes.
So I guess I'm wondering, right, is there like a different definition of entrainment that accounts for free-tropospheric relative humidity that gives a better understanding of what the actual cloud clear air interaction is?
Yeah, so that's a good question. The calculations here do account for that, and basically what they do is, so you imagine you got some conserved variable, and in this case, it's moist static energy. You have the moist static energy of a parcel in the updraft, and you have the moist static energy in the environment, and it assumes that they mix at the entrainment rate, and then you calculate what the resulting mixture, the new MSE of the mixture is. And that intrinsically accounts for, like, the MSE of the surrounding environment is strongly influenced by the relative humidity. So if the relative humidity is lower and those two parcels mix, you end up with less MSE in the updraft core, which means it's diluted. So it's sort of intrinsically or maybe implicitly accounted for in this framework.
What if most of the air that clouds entrain aren't actually the environmental moist static energy, but the moist static energy of high relative humidity?
So that's actually probably what happens. And it's sort of difficult to totally quantify, but yeah, so I'm talking about fractional entrainment rate. People have looked at direct entrainment, which is like the direct flux of mass across the cloud boundary. And that rate of entrainment is twice as high as what you'd get if you calculated the fractional entrainment rate. And it's because that air is sort of pre-moistened or maybe like previously, exhausted from the updraft, and then it gets pulled back in. So yes, that is going on. How it might actually influence these results. I have to think about a way to respond to that question. Yeah, I have like an idea in my head, but I feel like if I start talking, it's just not going to make any sense. So.
Any other questions?
Sure. Yeah, interesting talk. Definitely. We'll talk more tomorrow. When you're talking about changing climates, then you also need to be talking about changing environment as well.
Mm-hmm.
So any comments on that or ideas on?
So what do you mean by changing environment?
Well, the actual environment that a storm develops in could be different than what they commonly encounter today.
I had a similar question. I was thinking of phrasing it like we commonly think about climate change as wet places get wetter, dry places get drier.
Yes, I see what you're saying. So
yeah.
yeah, I mean, that was like, I didn't talk about that at all. There are studies of global climate model, like CMIP6 models, that show distinct trends in shifting in the positioning of storms over the US. And I think one of the most pronounced shifts is, severe weather becomes more pronounced during the shoulder seasons in the southeastern US and less pronounced in the central plains. So like, obviously this is not accounting for like changes in where things happen. One other factor though is there's some evidence that relative humidity should stay roughly the same. In the tropics, it should stay fairly consistent. In mid-latitudes, relative humidity is really variable, but you wouldn't expect the relative humidity in the free troposphere to go way up on average or way down on average. It's probably going to stay at similar levels to what it is now.
So in that case, you have these two competing effects, right? You've got the part that can make it harder to start these thunderstorms, but you also have the part that can make it sustain for longer.
Right.
And you think that impact from the warmer temperature is gonna actually globally, like speaking, overrule the fact that we might have higher RH entrained air to grow the storms large?
I don't know. Like,
So it's
honest,
a bit of a,
yeah,
which way will it go? Which one will be more globally important question?
I think a lot of this is just like a conversation starter, because basically, I mean, I'm often theoretical land here with these like, these little toy models that I'm playing with. This, like, I'm not even looking at GCMs in here. So like, I don't know the answer to that question. And I think it's going to take a lot of work to actually understand what the answer is.
Behind you first and we'll, or actually see if there's follow up. Yeah, go for it.
So, yeah, what you two were saying, that does sound like the conditions under which we get severe storms, the seasons, locations, and all would be likely to shift because of these differences in
Yeah.
interactions.
Yeah.
I think that's a pretty strong takeaway.
I was going to ask, the profile of the environment changed with the warming climate. So where did you, how did you obtain that profile?
Yeah.
And the other tagging along that is, the conclusion is that with the same entrainment rate, the updraft velocity become weaker, which means that, can I say that the relative humidity of the environment is lower as it gets warmer?
Those are
In the simulation what you made.
So those are really good questions. I held the relative humidity constant. I tested a range of RHs, but each time I increased the temperature, I held the RH constant. But the difference at a constant RH at warmer temperatures, the difference in the absolute amount of moisture between the updraft and its surroundings goes up. And that's the actual reason for why a given entrainment rate gives you more dilution at warmer temperatures. And then the second part of your question is, how do I generate the profiles? I had two different ways. One of them was just basically like pre-specifying a buoyancy profile and then fitting an environmental temperature that fit that buoyancy profile. The other one was I took a bunch of observed soundings in present climate from severe weather environments. I found ones that had surface temperatures at 295, ones that had surface temperatures at 305, and I made composites. Those that had roughly similar CAPE, and I made composites, and then kind of like linearly interpolated in between those two. And it's interesting, and so the buoyancy profile is not going to stay constant with warming. It will probably become slightly more top heavy. And you can actually see that in the present climate if you just look at the convective environments at different temperatures.
Was the tropopause fixed? Like your equilibrium?
In the experiments where I held the buoyancy profile constant, the tropopause was at a fixed altitude. In the ones where I used the observed soundings, it was not. The tropopause goes up. And so have you heard of the FAT hypothesis?
The tropopause is supposed to go up with warmer climate.
Yeah, fixed anvil temperature hypothesis. So it's unclear whether that applies in the mid-latitudes, but in the tropics at least, the temperature of thunderstorm anvils stays the same, not the altitude at which they happen. So the thunderstorms actually get deeper in a warmer climate.
Great. All right. Well, that will thank our speaker one more time for round of applause.